RISAConnection utilizes interactive connection modeling and visualization, including 2D and 3D views, for the creation of a variety of steel connections. In this video, let's take a look at designing seismic connections in RISAConnection. So let's go ahead and get started with a seismic connection. We're going to take a look at a sample connection of an extended end plate. This is the bolted extended end plate unstiffened connection. If I come over here, there's a setting here, seismic system. If seismic system is set to none, this would just be an ordinary wind type connection and then just meet the AISC 360 provisions. But in this case, we're going to take a look at this under seismic system as an ordinary moment frame, OMF, and then bolted extended end plate. Here we have some extra inputs now generated that we need to put in relative to the code. For example, shear due to gravity, VG, so we have this input to put in now. We can take a look down at the bottom of the screen anytime to see what this is referring to. We also need to know the clear span of this beam from flange to flange on the columns, and we need to know what the maximum moment that can exist in this connection. Now this is different from our design moments down here. So our ordinary design forces would be 100 kips here for shear, and then 1,000 kip inches for a moment. Let's just say that those are the forces that would be derived using our seismic base shear equations, where we're using the OMF that has an R value of 3.5. If we want the system to remain entirely elastic throughout, we need the design for the forces that are 3.5 times what the seismic base shear would tell us. In other words, instead of 100 kips, we need to design this for 350 kips of shear and 3,500 kip inches of moment instead of 1,000 kip inches. Let's take a look at this connection as it currently stands right now with its existing design. If I come into the reports, we're going to see a number of pass and fails, but let's look specifically at the seismic moment at the face of the column. In the case of an ordinary moment frame, this is just a direct input of the 3,500 kip inch that we need to design for. We also have some NAs reported here. Under seismic width to thickness ratios, this is the limiting width to thickness ratios per AISC 341. We see an A because this limit state is actually not necessary for ordinary moment frames. This must be checked for higher level seismic systems such as the IMF and SMFs. But for the OMFs, it is not necessary. RISAConnection reports these such as the column beam to moment ratio so that you're aware of them, but this is just for your own reference. This is not needed to be met for the pass-fail checks. Let's take a look at some of the limit states that might control. For example, seismic end plate flexural yielding. What we see here is we've got a demand and a capacity overstressed issue. If I click to expand this, we can see here the code equation for the AISC. We can also see on this equation what goes into the strength calculation for the seismic end plate. We're using a 36 KSI end plate, but let's go ahead and bump that up. Now we can change the grade to be 50. Now if I go back to the end plate flexural yielding, we'll see that our overstress has decreased. Under the thickness property, I'm going to bump up the thickness of the plate to be 7/8 of an inch. Now our end plate flexural yielding is passing, and we're on our way to getting this connection to work. At this point, we reviewed the modeling tools and designs available for seismic connections in RISAConnection. For more information on other topics, please visit our website, risa.com.